So, welcome to the Setting Up Triple Resonance Experiments tutorial. I'm Julia. I think most of you have talked to me. I'm also from Frankfurt, from the BMS lab there, from large infrastructure like here. Same group as Christian. And we will go together through the triple resonance experiments today. So, I will have an introductory part, a little bit about remote NMR. That's because we will do this remotely. We will set up one experiment, 3D experiment. We will talk about the processing and do some assignments with Kara. So, why bother with 3D NMR? Because if we look here at this spectrum, it's great, we don't see this. You don't see my laser pointer. So now you see it. If we look here at this 2D spectra, it's an H-C carbon-proton correlation spectrum. We see there's lots of overlap. So we can't really say which peak is which. So we need to go to a higher dimensionality, to the third dimension, to resolve these peaks. Further, a 3D experiment makes possible to assign a proteins via 1J and 2J coupling constants. That is very straightforward. So even if this would be resolved, it would be very difficult to assign this in a two-dimensional manner. But going to the third dimension, this is really straightforward, the assignment of a protein. And you need to assign a protein not only if you want to have a structure like Francesca presented yesterday, but also if you want to if you look at relaxation data that Antonio presented today and that you will learn the analysis with Laura just later, then you need to know which peak in the HSQC belongs to which amino acid, so it's very good to have an assignment. And these 3D experiments make assignments very easy. Francesca yesterday already showed you the 3D experiments, and I want to dwell on two of them. The HNCACB is one of the 3D experiments that I really like a lot, and the HNCO, because the HNCO is the easiest 3D experiment that we could think of. So we start with the HNCO. In the HNCO, you basically start on a proton. You transfer the magnetization from the proton to the nitrogen, then from the nitrogen to the carbonyl carbon, and then back to the proton. That's the errors that you see here. And doing so, you can record the chemical shift of the proton, the chemical shift of the nitrogen, and also the chemical shift of the carbonyl. And what you then get in the 3D experiment is one signal that if you look at if you look at the amide in the HSQC, then you get in the third dimension the carbonyl chemical shift of the -1 of the carbonyl from the residue that was before that. So you get one peak for each amino acid in the 3D. That's nice to see, nice to analyze, but from the first place, you don't know which carbonyl carbon this is. But it's from the concept, I think this is the easiest. A little bit more complicated is the HNCACB. There you also start from the amide proton, you transfer the magnetization to the nitrogen, and then you transfer magnetization to the C-alpha carbons. And you can go to the own C-alpha carbons because you have a coupling constant of 7 Hertz there, of 12 Hertz here, to the own C-alpha carbon from here to here. Or you can go to the alpha carbon from the -1 residue, because this is also quite similar, the coupling constant, that's 7 Hertz. So you do one transfer step, and in this transfer step, you go either here to the own C-alpha or to the previous C-alpha carbon. And in the next step, you go from the C-alpha carbon to the C-beta, both of them. And that way you basically get, for each of the amides, you get 4 signals in your 3D. You get the signal of the own C-alpha carbon. This would be this. You get the signal of the own C-beta carbon. this would be this one, you get the signal of the previous C alpha carbon and the signal of the previous C beta carbon. This previous C alpha carbon would be this, and the previous C beta would be this. As you can see here, some of the signals are bigger than the others. So the own signals are usually bigger than the signals of the -1 carbon. And this way, you can go through this 3D experiment and in the first step, pick all the peaks and say, okay, the bigger peaks are the peaks of the own residue, and the smaller peaks are the peaks of the -1 residue. And if you have done this, you then can basically compare all these strips, we call this strips, these things, you can compare all these strips and put them in an order and say, okay, this strip must be behind this because here I have these two that fit so nicely. I have here this own peak, the big peak, and here I have the smaller peak that's at exactly the same height, so I know they have to be behind each other. And that's why we make 3D spectra, and that's what's nice about 3D spectra. Okay, so I said the HNCO is the easiest of the 3Ds. So we have here the HNCO again. This is the pulse sequence of the HNCO. This is how the NMR spectroscopists like to draw their pulse sequences. So if you see this, then if you're an NMR spectroscopist, you know, okay, here's an inept step from basically here, the red line to the next red line. And in this step, I transfer the magnetization from the proton to the nitrogen. In the next inept step, and you see here, we have always some delays. And in the middle, we have these more broader pulses that are 180-degree pulses. In the next step, I have the same pattern. In the middle of this delay between the three, I have again the 180-degree pulse. This is another inept. Here, I transfer the magnetization from the nitrogen to the carbonyl. Next step, it looks a little bit different. I don't have this pattern again with the 280-degree pulses because here I want to evolve chemical shift. I want to record one of my indirect dimensions. So here I record the carbonyl chemical shift, and afterwards I transfer the magnetization back. I can again see this these two 180-degree pulses that are at the same time, telling me, okay, this is again an echo sequence, an inept. To go back, now transfer the magnetization from the carbonyl to the nitrogen again. In the same time, I have these other delays, the D10 here. This is good for the evolving of the nitrogen chemical shift. I will go into this in a second, in the next transparency. And here in the end, I transfer the magnetization back from the nitrogen to the proton, again with these inept steps, with these 180-degree pulse echo sequences. In the last step of the HNCO, I record my spectrum on the proton channel. This is shown here. In the software in TopSpin, you can always look at the pulse program in the pulse program tab. That's here. I think you can't really see it, but if you have TopSpin in front of you open, then you can probably see this. You don't have to open it now, but then it's a bit bigger, I think. So you can always look at the pulse sequence, at the written pulse sequence in this TopSpin thing, and in the pulse sequence you have some information. So you have, for example, information about the transfer delays. You have information about incremented delays, increments, calculated delays. So you get a whole bunch of information in this pulse sequence before you really start pulsing. So I would like to look a little bit in this part of the pulse sequence, just as an example, how this would look like in the pulse sequence programming. So this was the part where we are on the nitrogen. We are on the nitrogen chemical shift, and we record the nitrogen chemical shift. And basically what we do is, for the nitrogen chemical shift, we record this during the time D23 minus the time D10. Is always a delay, it's always a time, minus delay D10. Then we have an inversion in 180-degree pulse, and we go basically back in time. So we have to subtract this, what stands here, so minus D23 plus D10, that's here. If you do this calculation, this very easy calculation, we see, okay, in the end, we end up with 2D10. So 2 times D10, we evolve the nitrogen chemical shift during this time. We can look at the coupling, the carbonyl nitrogen coupling that we have to get rid of during this time. And we can do the same calculations here. And we end up with realizing that the coupling evolves for this delay D23. This is exactly what we want to have. Can also look at the coupling between the carbonyl and the carbon, the C alpha, the nitrogen and the C alpha. Sorry, here this is wrong. And if we do this calculation for this, following these pulses, this pulse and this, then we would see that this doesn't evolve at all. And this is exactly what we want to do. And we can look at this like this. But if you want to go more into detail with this, I can do this and explain this very detailed. But I'm not sure that if this is your focus. So I would probably rather go forward. I just want to tell you, you can do this, and you know that this is possible. Exactly. So more to this pulse sequence. This is again from this pulse sequence thing. And at the bottom of this pulse sequence text, you have information about pulses. And this is interesting if you want to set up something and you have no clue what is this pulse about and what is it doing in the pulse sequence, then sure, one possibility is always to go to the whole pulse sequence and understand everything. This might be difficult sometimes. But most time, at least if it's standard pulse sequences, in the end you have this legend and it says, okay, for example, this SP3 is the F2 channel. So the second channel, it's a shaped pulse, 180 degree. It's for carbonyl on resonance. So then you know, okay, this is this pulse. Okay, at this point, I still don't know what to do with this, but I can at least say, okay, this is for this pulse, the same thing. P14, F2 channel 180 degree shaped pulse. I know, okay, these two apparently belong together. And I see this here in the pulse sequence, P14, SP3, and I also see this in the written part. But that way I can basically go through the experiment and figure out what I have to set later if I would set the parameters all by myself. What parameters are there to set? You have always have to know basically the chemical shift of the involved nuclei. That's protons, carbons, and nitrogens. In this case, you need to know the spectral width. I come to this when we have set up the spectrum, why we need to know the spectral width, why this is important. We need to have the pulse lengths. I think you had this 1D acquisition tutorial practical, so you basically know that you have to determine a pulse and how to do this. So you have to determine this beforehand and set this properly in the pulse sequence. And you need to know the coupling constants so that you can do the transfer from there to there in an efficient way. Some typical parameters for backbone assignment experiments are found here. So here you have the coupling constants that might be involved in whatever experiment you want to do, a triple assignment. Backbone experiments, so 7 Hz for the 2J NC alpha coupling, 12 Hz for the 1J NC alpha coupling, or 14 Hz here for the NC carbonyl coupling. That's the experiments that are relevant today, maybe. Then you have typical offsets. For water, it's usually 4.7. The amide protons resonate around 8.3 ppm. Typical spectral widths for the nuclei that are involved in the backbone experiment. If you now don't have a spectrometer at your place, or not a very nice spectrometer, you need high field, something like that, then you can apply for remote measurement time at research infrastructures, for example here or in Frankfurt. So there were three possibilities that came to my mind, but I think there are more. Florence is involved in one more. So you can apply for measurement time either via iNext or via the Instruct network, or in the Panacea network, that would be only solid state. The other two have solid state and liquid state NMR, and then you can apply for measurement time somewhere. And either you travel then there, bring your sample and do it with a local operator, or you send your sample there, and then lots of times the local operator will just set up the experiment for you and then send you the data. But it's also possible that you basically do it yourself remotely.
And how does this work? Like we have a specific transfer there to pay for that NMR time, or?
Yes, exactly. This is these research aid. This is these research programs. It's INEX Discovery is a European grant, for example, that had been written to have access for people at these spectrometers. So basically, we are in Frankfurt. We are part of this INEX Discovery grant. So we get money if somebody from outside comes and measures at our place. And that's advantageous for us because we have to keep our spectrometers running. So that means we have to buy new software or new hardware from time to time. And yeah, so this is really advantageous for both sides. So for the person that can come and measure, and the EU pays it, or instruct. I think also for outside EU users, this is paid. Yeah, so this is really nice. And I think tomorrow the last session is also how to apply for this measurement time. Genau. So yeah, as I said, I will a little bit dwell on what is important if you do something remotely, set up remotely an experiment. So if you want to set up an experiment remotely, then you have to first, and I really want to emphasize this, if you have the possibility of lots of spectrometers, then first check that you're really on the right spectrometers, because if you walk in a room, you see directly, oh, this is my spectrometer. But if it's only a computer, it always looks, the remote screen always looks the same. So make sure that you're on the right spectrometer and don't stop anybody else's experiment, something like that. Also check in the computer, are there any error messages that could tell me that there's something wrong and I won't get any results. As always, you have to create a data set, read parameters, select the proper measurement temperature. Important, before you enter your protein, there might be a protein that denatures at whatever 40 degree. I have one that denatures at 40 degree, and then if your measurement time, if the person before you measured at 40 degrees and you just put your sample in, then this is very unfortunate, because then your sample might be gone and you don't get it back. So first select the proper measurement time, then insert the sample. In some kinds that you might need some help from a local operator in this case if you do this remotely, because the temperature unit might be that you have to enter cooling manually to switch this on if you want to measure below whatever 288 Kelvin. And also if you don't have sample changer, somebody has to put the sample in manually. So you might need the help of a local operator if the instrumentation is not super modern. So the modern spectrometers can do all of this themselves, but in Frankfurt we have both. We have some that can do everything themselves and some that we need to have a person who switches on the BCU and puts the sample in. Okay, so then you have to log, set the correct solvent, tune and match, and if the probe has no ATMA, this also has to be done manually. You have to shim your sample as always. You have to determine the pulses or load pulses from a background table. Check and adjust pulse sequence specific parameters and adjust the receiver gain. Before you run a 3D, because this is about 3Ds, please check the spectra of the sample, because yeah, it's a waste of measurement time if your sample is not in a good shape. If it had I mean, it could be that a couple of days ago you looked at your sample, it was nice, and now you put it in the spectrometer and it has degraded, or yeah. So please look at the 1Ds and look at an HCC before you run a 3D experiment. So what could go wrong? The sample is maybe okay, but you have poor signal to noise. And then this could be because the sample concentration is just low, but then you have to run some optimization spectra by hand and put optimized values yourself and run a 3D with high number of scans. That's not, if it's not too low the concentration, that's not a big deal, but you can also have poor signal to noise because the sample is not properly folded. That is done, unfortunately, and then you have to go back to the lab and do some optimization. Who was this morning? Yeah, we heard this morning about the optimization, what you can also always optimize. You can play with the temperature, you can have different salt conditions, different buffer, different pH. You might want to consider sample purification, again, higher or lower concentration. So this could also always be a reason for poor signal to noise. What you can also see if you check the HSQC, you can have impurities or you can have very broad lines, and or you can see that the sample is not properly folded, that you see an unfolded protein where you expect a folded one. So then go back to the lab, spend a week or two or even a month on optimizing this before running 3D experiments that won't be of any good. So now if you want to really set up the 3D experiment, as I already said, always check the integrity of your sample before running a long experiment. You can have basically two ways how you set up the experiment. The standard way would be you determine the pulses, protons, 15N and carbon pulses. You record a 1D and an HSQC to check the sample integrity. You read standard parameters sets from the Bruker pulse sequence library. You do that with R-NMR. You set the pulses. You check the parameters again. If in the standard sequence the offsets are properly set, and you check this. You press RGA for receiver gain, that you have a good receiver gain, don't have overflow, don't have too little receiver gain. You run planes, you run planes of your 3D, and then you start your 3D. This is what a more experienced user would do. Or if you're not that experienced, you would use Biotop, and this is what we just will do in a second. This Biotop is really nice, and I have to admit I didn't know it, just got to learn it. And this does all of this, what you can do here on the left side, it does it for you, and it does it in a very nice way. It's not that the user does it better than this program, so it's actually really nice, and you can also look at the results and see and check if you would have done this the same way as the program. So I would advise to use this because it's really nice. This program does all these optimizations that you here can do, determine the pulses, set the right pulses, set the spectral width. It does all for you. You can check this optimization results. It does RGA and it starts the 3D. So this is a really nice thing. It's very, very brief. How does this program look? You open it by typing Biotop in Topspin. You get the first page where you have a sample information. You have basically, this is only for you, molecule name, a description. Then you have here an optional part that you don't have to fill out, but it's really nice for relaxation analysis because this way, this is not for the 3Ds, but just to be complete with the Biotop. You can put in the sequence of the protein, a PDB structure, and also the assignment. And if you have all this, you can later automatically run your relaxation spectra and have plotted the results on the protein basically with one click. It's really nice. What you really should put in is the molecular size of your protein, the labeling, and the solvent, because these parameters are basically used to suggest which experiment you should run.
Is labeling necessary for 3D?
Yes, yeah, it's labeled. You have to have, if you want to have run a 3D, you have to have a nitrogen 15 label, and yeah, it would also a carbon 13 label. So there is basically the exception. You can have a very, very thick sample with carbon 13 label, unlabeled carbon, and then record an HNCO in natural abundance. But this only works with a very thick sample with a lot of measurement time. But for all the other 3Ds, it wouldn't work to do this natural abundance. So you really need labeling scheme. So you put this in to have the program work best for you. Then, as I said in the general how to set up an experiment, you have to set the temperature, you have to log, you have to tune, you have to shim before you run any experiment. This BioTop can do this for you. So you basically check these buttons, and then it does everything for you, and you don't have to do it yourself if you're lazy. As I already said, it can do the optimization of all the parameters that you need for the 3D. So that this is the pulse lengths, the hard pulse lengths for protons, for nitrogens, and for 13C, the spectral width for the 15N, for example, or the carbonyl and the carbon. You can always check this auto-optimize, and then it will do it for you. You will get results, and within TopSpin, it makes all these directories with the results of the optimization, and then you can look at these results and see, oh, is this really the spectral width that I would have set as well or not? So this is very convenient. You can also have a PDF file where it then tells you all these optimized pulse length and what he got out as a result from the optimization. The next panel we have these panels here. We had just the optimization panel. The next panel is the experiments panel. And in the newer version of BioTop, it will also suggest you some experiments depending on which labeling scheme and which size of your protein you have put in the first page. And in addition to the suggested thing, you can just open a protein tab and then select backbone assignment and then choose which experiment you want. The experiment you want, you basically mark it, press add, and then it appears here in this tab. If it has appeared in the tab, you can always edit some of the parameters in the of this experiment, and you can also double click on this experiment here, and then it will open it in TopSpin. I said previously, I said, oh yeah, then you choose some experiment, and then there you see here is backbone assignment, and there are a lot of experiments to choose from. There's echo, anti-echo, Watergate, TOSY, best TOSY, 2H decoupled. So there might be the question, which of these options should I choose now? All of these 3D experiments are HSQC based. That basically means if your HSQC looks nice, well, if your HSQC looks horrible, then your 3D will also look horrible, probably, or it will look horrible. So you can basically run a couple of HSQCs before you start running your 3Ds, and then say, okay, which HSQC is best? Then I use this scheme for my general scheme for my 3D. And here are the most common HSQC, an echo, anti-echo HSQC, and Watergate HSQC, and you basically look at the spectrum. What you see here, you have here the water signal that you see. You don't see the water signal here, but if you look here, the intensity of this signal, which is close to the water, here would be the water, is also lower than this. So this way you can see, okay, is this maybe better or this better for my problem? Yeah. And in this Watergate, you really do water suppression with pulses here selectively on water, and you don't do this here because you basically select your magnetization by gradient selection. So then there are more experiments. So that was the echo, anti-echo, and the Watergate. Then you have TOSY experiments. TOSY experiments, here. TOSY experiments are transverse relaxation optimized experiments, and in these experiments, you use these experiments for big molecules, because big molecules are very broad, because you have so many different relaxation mechanisms that really kick in for the big proteins, and there you have in each peak is then not only one peak, but it's basically four, has a pattern of 4 big peaks, and this way you choose the very big peak with the pulse sequence, the very big component of this peak, and you don't touch the other components, and that way you get a very nice spectrum even for bigger proteins. So this I would advise to use the TOSY for big, large proteins. And then we have the last thing that would be the best option. And in the best option, you excite only the nitrogen protons in the beginning. You don't touch the others. You don't touch the water. And this way, you can make the delay between experiments a lot shorter, because the T1 time is a different one. And then you can make a lot more transients, a lot more experiments in a shorter time. So this is a very nice thing to save time if you want to run a 3D without sacrificing signal to noise or something like that. So, okay. Yeah, that's basically biotop. But some people will always say, oh, I'm not trusting this machine that does everything for me in a black box. So you always have in biotop also the option to go to the acquisition panel of the TopSpin and look at all parameters that are there. So it's not that you don't have to use the black box, you always can, but you don't have to. That's very nice. And with this, we go to the spectrometer and look a little